Okay, welcome from my side as well. I'm Markus. I'm a professor at Vorarlberg University of Applied Sciences. And as I have a lot of hats on at the university, I just say the most important thing today, I'm the head of the Josef Ressel Center for Intelligent Thermal Energy Systems. And this is the project I present today, or at least I present one part of the project. With one industrial partner, and I called it so much data, so little information, or can pure data serve as digital twin? That was the questions I want to answer to you a little bit. See if it works. Yes. Basically, we have a lot of data. That's the most important thing, I think, for every digital twin. In our case, we have data from 2 biomass power plants of our industrial partner, Berge Energy. We have a third one right now, and we will get a fourth one in the future. Basically, for CHP 1 and 2, the data is available just in a data acquisition system, which we have to then export into Excel files and then re-import into Python again. For CHP 3 and 4, we will have it already in the cloud because the systems, so the power plants are already connected to the cloud. So that makes it a little bit easier for us. But basically, we have a lot of data, and Berge Energy told us, okay, can you give us an additional value out of this data? And we said, yes, we want to focus on predictive maintenance. So basically, our digital twin, first of all, the intention is to have a predictive maintenance system in the power plants. So we collect data, we pre-process data. Let's just do the laser pointer. We pre-process data, we detect anomalies, we estimate degradation, and we calculate the remaining useful lifetime. So this is based on data-driven approaches, on knowledge-based driven approaches, or on physical-driven approaches. And now the question is, when comes the digital twin? So basically, at the moment, we are just reporting what we find to Berge Energy, and Berge Energy decides if they are reporting it to the plant operator. To make a real digital energy twin, we should react within the system. So at the moment, we are going this way to the reporting, but I will show you that it would be an opportunity to react as well, and which is the reaction, or what we call reacting on the topics afterwards. But first of all, I want to have 3 or 4 slides on this topic because that's the core of the knowledge we are increasing for the company. So detecting anomalies, estimate the degradation, and calculate the remaining useful lifetime. And I brought you one example, a water treatment system. So I'm pretty sure that not everyone here is familiar with thermal power plants. Just make it easy. You have normal water here, and you need desalinated water for the turbine at the right-hand side. And in between, there are a lot of purification stages. So we have cation exchanges, we have reverse osmosis units, we have an electrode deionization, we have a tank, and afterwards we have a mixed bed filter. And the company told us, so Berge said that although they designed the whole system, that one mixed bed filter can last for about 180 days in operation, in full load operation. Sometimes the mixed bed filter have a higher salinity that is allowed after, let's say, 30 days. And they told us, okay, find the failure in there and tell us what we can implement then in our systems as predictive maintenance. So what we are going to do is we combine data from the power plant and combine it with knowledge from a plant engineer who is a PhD candidate at our university. Here is the data. Don't worry, we don't go through every point here, just to 50% of the points. So what we basically want to do is we want to say, okay, here everything looks normal. Look at the lowest point. We need a salinity of 0.1 microsiemens per centimeter. And here the blue line is the value, and all the points that are green are fine. So the turbine is working perfectly fine with this salinity. What the problem is that at a certain point, we increase here the salinity, and we see it already here in the electrode deionization that some points are here not green anymore. So for the reverse osmosis 1 and 2, everything looks good, except of this small increase here. For the electrode deionization, we have a problem the whole time. So this is a combination of data and expert knowledge. Of course, we can just tell about the threshold values, but we can also say, no, this threshold value is not a problem at the moment, based on some expert knowledge, if we know a little bit more about the power plant. But what we actually want to do, we want to see this increase, let's say a few days before, because then they can switch to mixed bed filter or regenerate one mixed bed filter to switch it afterwards to the second one, that we don't have problems with our turbine. So we want to foresee, let's say, this increase in all the values. We said that, or I already told you that the electrode ionization is the problem. We saw this, and here you can see it a little bit more clearly. Just to give you an idea, the reverse osmosis 1, the green dots should be less than 8 microsiemens per centimeter, so it's almost okay. The reverse osmosis 2 should be also less than 8 microsiemens per centimeter, that's fine here. And the electrode ionization should be less than 1 microsiemens per centimeter. And you see that the values are far higher, so sometimes by a factor of 5 or 6. And so we used some approaches from data science and analyzed especially this part here. And if you do the simplest thing ever, you just integrate all the values here for the days, then you can say, okay, if you know that in a perfect condition it will be 180 days, you can just calculate that with this value of the electrode ionization, you come up with a value of 16 days. So we calculated 16 days and the failure occurred after 21 days. So we gave the plant operator 5 days in advance to regenerate basically the mixed bed filter. And now, until now, it's not a digital twin. Until now, it's just a data-driven and knowledge-based analysis of a thermal power plant. What we do now is we report this value to the batch energy and they report it to the plant operator, and the plant operator reacts in their Siemens system. So in their control unit, they react and say, okay, then switch earlier to mixed bed filter 2 instead of mixed bed filter 1. So basically, we do a reporting, but we are not reacting. Reacting would be, so the automized reacting would be then the digital twin. But I think we are able to do. So if I want to summarize the short presentation today, and being a little pathetic, not the typical bullet points summary, I think we have the data available, the computational power necessary, as well as the knowledge in engineering and data science to say so much data, so much information. So we got 450 values, sometimes with a resolution of milliseconds, but we can actually find some information which is valuable for the plant operator. Just keep in mind, we are talking about power plants with a power of 20 megawatts. If you shut down a power plant of 20 megawatts for 3 days because the mixed bed filter is full, then just multiply 3 days, 24 hours, multiply 20 megawatts, and you can calculate the kilowatt hours you're not selling. That's a lot of money. And this is what we find in the data. However, we do not have a digital twin at the moment because we are not reacting. And this is the outlook for the next 3 years in the Result Center. We could have, because to react, you need a data acquisition, you need a front end, and you need a back end. And afterwards, you need a connection to the control system based mostly on Siemens and stuff like this. In the new power plants 3 and 4, we have a data acquisition system of our partner Gunstra Instruments. So we have all the data connected to devices like this. We get all the data automatically into a front end. So we see all the data in plots and stuff like this, have all the data here as time series available. And we have the backend. We have a connection to a Jupyter notebook, and we are using Python to analyze these data all the time. I don't want to call it real time because there is a certain delay, but we do it constantly. And if we combine now things we see in the Python code or in the data analysis, if we combine this to the Siemens control system, we could say if a value here is too high, shut down a pump or something like this. At the moment, we are doing this, and then we are doing a reporting. However, if the customer says, I want to connect the Gartner Cloud with the Siemens interface, I think Gartner would be able to do this, and then we would have a full digital twin. At the moment, we don't have a full digital twin, we have a full digital reporting tool, let's call it like this. And the next step would be a digital twin if the customer wants it to be. But I think in this round, we all know the problem. Sometimes customer says, okay, you can report me automatically, but you do not change my process automatically. But if they want, I think we would be able to do it in the last 3 years of the project. And of course, I have to thank the ministry for all the money we get to do such crazy things. That was already it from my side.
Thank you, Markus. That's a very interesting take on digital twins. So basically what you're saying is that like you can like build a digital twin by just having a cloud and data processing algorithms.
And a lot of knowledge.
And a lot of knowledge. That's the important part, of course.
Yeah, that's the important part. Therefore, I hired a power plant engineer from Russia as a PhD candidate, because they know how to build power plants.
Nice. Arnaud, you have a question.
Yes, thank you for the presentation. One quick question I have, it was not clear for me. When you're looking at the remaining useful life, I'm not sure if you mentioned that you're using only data-based or physics-based or combination of both. Could you give me more details on that, please?
Yes, so basically in this example for the remaining useful lifetime, we just said, okay, the mixed bed filter was designed for 180 days with a value of less than 0.2 microsiemens per centimeter. And we saw that the value which is normally active is about 2 to 3 microsiemens per centimeter. So it's the easiest physical model you can have. You just say, okay, the one thing is 0.2, 80 days, the other is 2.5, so you come up with 16 days. In the future, for other components, we also want to include physical models, so easy physical models. Let's say for a pump, if we see that the temperature is increasing, you can have a physical model that shows if the temperature is that high, you have isentropic efficiency that is lower than 0.5, and therefore the pump is destroyed or something like this. So it's always basically, you always have to decide between, do you want to do it knowledge-based, data-driven or physics-based? And in this case, we use some knowledge from the design of the mixed bed filter and some data. But we don't have a physical model in this case.
Okay, just for information, that's something the physics-based and combined physics and data-driven. That's something that we did for one of our customers, so we could help you or guide you in how we did it and how it could be done.
That's interesting. So if you have any conference papers or international journal papers, I would be more than happy if you send me those so that I can.
Unfortunately, as we're working with customers, we're not allowed to do those publications, but we can plan a call and share with you our insights. Even if they're not in a white paper, we can still tell you how we did it.
Okay.
Yeah, we have a few high-level presentations.
Okay, perfect. Thank you.
My pleasure.
Say, what do you think? How well does this approach sort of scale? Say if you have a power plant that has like a lot of problems, or not, there's like a lot of optimization potential. Let's frame it like that. Would you just go and start designing these data-driven approaches for each of the issues at hand, and try to come up with the right data treatment and thresholds for various numbers?
Yeah, so that's hard to answer. I answer in terms of the company who gave us the money for 5 years. They told us that their intention is not to use it just in one single power plant, but to adapt it easily to other power plants afterwards. So they told us they don't want to call us after 5 years for each and every power plant, okay, please adapt the code. We should come up with an adaptable code that is so easy to adapt that they can do it on their own. And therefore you need really easy physical models, really good documented, that you can say, okay, if you have a pump in a new system, and if you have the temperature sensor there, just put in the new temperature range or stuff like this. And then you can easily adapt it. So that's the idea. We see already that something we developed for CHP2 is not possible to use it for CHP3 because they are too different. However, even if in power plants you're more in a you're going more in the direction that you're doing modularization and use certain pumps or certain boilers for more than one power plant. And therefore it should work to adapt it to different power plants.
Mm-hmm.
But there are always problems which are just in one power plant and they never had, and then we just have a look on it, but then we are not talking about the digital twin. So the digital twin for us is more an online monitoring system, a constant online monitoring system with a reporting tool in the background.
Thank you. Are there any more questions? Or maybe does anybody have experience with this kind of approach, like just doing data science or like building a digital twin just with data? Has anybody else tried this and has it worked out? Seems to be a novel approach.
Therefore, we need 5 years and a lot of money.
Yeah, sure. I think this is really interesting because we are taking a completely different approach. Here in Digital Twins, we're going really deep into the physical modeling side and try to connect the physical models with the data. And you're sort of on the data and knowledge side. This is like, it's really interesting to see what you can achieve with a completely different approach.
Yeah, and just to give you an impression, one last paper of the PhD candidate in his doctoral time of the 3 years, he wanted to compare at the end of his PhD how for one specific part of the power plant a physical model works and how the data-driven model works and how it is compared. So it will be interesting to see if we come to a accuracy of the data-driven model that is good enough for a power plant operator, or if we have to include more and more physical models as well. Yeah, but we start with the data, you start with the physics and try to make the physical models as easy as possible. We start with the data and try not to use physical models at all at one point.
Mm-hmm. Interesting. Now, I'm going to look up the paper. Or it's not out yet, is it?
It's not out yet, but it will be. In the conference where we presented is in April for the water treatment system, and then hopefully now every year at least one additional paper will be published on this topic.
Nice, nice. All right then.